In this session, we will learn acoustic and language models in general speech recognition system. The figure shows a block diagram of a speech recognizer. The preprocessor converts speech waveform into a sequence of feature vectors at short intervals. For example, 10 milliseconds or 20 milliseconds. Acoustic model calculates the probability density that an observed sequence of feature vectors corresponds to a particular word sequence. Language model estimates the probability of a word sequence. A likely word sequence has a low probability. Hypothesis generator try every possible word sequence in turn and choose the one with highest score. It is a huge task and is essential to have an efficient algorithm. The acoustic model is to classify the acoustic features of the speech and decode them to the units such as phonemes or words. The language model then decodes the word into a complete sentence. The acoustic model must give the probability that the model generates the observed feature vectors in response to the word sequence. Acoustic model is just to compute the probability of uttering one speech segment after given the text. How can we know what sound each word sounds? This requires another model called a dictionary. Dictionary is used to build a bridge between the acoustic model and the language model to connect the two models. Feature extraction in the preprocessor is sometimes included in acoustic model. Feature extraction in acoustic modeling incorporates knowledge of the nature of speech sounds by marrying the features and utilize the models of human perception. Typically, it measures features 100 times per second from the input speech and uses a 20 millisecond window for frequency domain analysis. After spectral analysis, the output features include absolute energy and 12 spectral measurements. Then, time derivatives with energy and spectrum are used to model the energy and spectral change. Traditional speech recognition systems usually use male frequency spectral coefficient, MFCC, or perceptual linear prediction, PLP, as features, and use Gaussian mixture model, hidden Markov model, GMM, HMM, as an acoustic model. In recent years, discriminative models such as deep neural network, DNN, have shown better results in modeling acoustic features. Acoustic models based on deep neural networks have greatly surpassed the past GMM-HMM model in the field of speech recognition. In GMM-HMM acoustic model, HMM is used to model the timing information. Given a state of HMM, GMM is used to model the probability distribution of the feature vectors belonging to that state. With the development of deep learning, DNN model replaced GMM for HMM state modeling. Different from the GMM model, in order to obtain better performance improvement, the DNN model introduces context information. So it is called CDDNN-HMM, context-dependent DNN-HM model. Language model is used to estimate the probability of each word given prior context. The number of parameters required to compute the conditional probability grows exponentially with the number of words of prior context. To solve this problem, we introduce Markov assumption, which assumes that the probability of the current word only depends on the previous n-1 words. Thus, we get an n-gram model using only n-1 words of prior context. The Markov assumption is the preassumption that the feature behavior of a dynamic system only depends on its current history. In particularly, in a k-order Markov model, the next state only depends on the k most recent states. Therefore, an n-gram model is a n-1 order Markov model. In theory, the larger the order n in the n-gram model, the better the performance. Generally, n-gram models include 3 common forms: unigram, bigram, and trigram. Trigram is the most used, but if bigram can be used, trigram is not used. Language model is an important technology of natural language processing. The most common data in natural language processing is text data. We can think of a natural language text as a discrete time series, that is, word sequences. Language model is to compute the probability of the word sequence. According to the chain rule of probability, we need to calculate the probability of a word and the conditional probability of a word given the first few words, that is, the language model parameters. In order to lower the complexity when computing the probability, we use a Markov assumption to obtain n-gram assumption. Different order of resulting Markov model form into different n-gram models. Unigrams give the probability of a word in the absence of any context. Bigrams give the probability of a word as a function of the preceding word in the sentence. Trigrams give the probability as a function of the preceding 2 words. As shown in the table, with larger n, a model can store more context with a well-understood space. For example, if there are 10,000 words, there will be 10 to the power of 8 different bigrams and 10 to the power of 12 different trigrams. But most trigrams will not appear at all in the training data. Generally, we use trigrams or quadgrams for common word sequences, and bigrams or even unigrams for less common sequences. HM-based speech recognition has 2 main stages, including training and recognizing. Training stage aims to estimate the parameters of acoustic and language models. The recognizer or decoder converts the input speech feature sequence into a character sequence based on the dictionary. The acoustic model and the language model. The pronunciation dictionary or lexicon contains all the words in the system's vocabulary along with their pronunciation. Often, there are multiple pronunciations per word. and each word pronunciation is marked. The dictionary obtains the mapping relationship between acoustic modeling units such as phoneme, and language modeling units such as words, thereby connects the acoustic model and the language model for decoding. In Chinese, it is the correspondence between pinyin and Chinese characters. In English, it is the correspondence between phonetic symbols and words. The purpose is to find the corresponding characters or words based on the phonemes recognized by the acoustic model. The acoustic model uses HMM to represent the basic sound units that the system is capable of recognizing. The language model determines the possible word sequences allowed by the system through encoding knowledge of the syntax and semantics of the language. From the view of layered architecture, the recognizer firstly converts the input acoustic signal waveform into speech feature vector, and then estimate the possible states, phones, with acoustic model. The pronunciation dictionary is used to map phones to words. Finally, language model output the most possible word sequence or sentences. There are some constraints utilized in automatic speech recognition. Acoustic speech signal is generated by the human vocal apparatus, which contains some pronunciation features. There are some phonetic or phonological rules we should pay attention to when describing pronunciation mechanism. Words in a language are limited. Therefore, some unlikely word sequences can be eliminated from the search to make the decoding complexity lower. For the language model, the probability of a word depends on its predecessors. For example, in English-speaking, you is the most likely word to follow thank. A sentence must be syntactical and semantical well formed. For example, subject-verb agreement. That's all for this session. See you next session.